Okay, so now that we've established the basic shape of the current versus, the source drain current versus source drain voltage curves, and we've motivated why the saturation happens, let's look quickly at how to find the different quantities for the device. So first, let's look at how to find threshold. So in order to determine the threshold voltage, we actually want to plot the I source drain versus gate voltage. So this is different than the plots we've been making. And basically, you're going to have a region where it's linear, and what you do is draw a straight line through that region down to 0 and call this your threshold. Of course, the transition, there's no such thing as zero current running through the device as long as you have a finite drain source. There's always going to be some leakage, and so you have to sort of do an extrapolation plot to determine this. So the slope here is from our previous equations. In the small source drain voltage regime, the slope is di source drain versus dVGS, and this equals the width, oxide capacitance, the mobility over 2L, and then times the source drain voltage times VGS minus V threshold times, VDS. So we've just done some simplification there. Okay, so in the saturation regime, the current depends slightly differently. So VDS greater than VDS sat. You end up plotting the square root of the current, and when you do that versus the gate source, so let me draw a dividing line here. ISD square rooted V gate. So now you can also find a linear behavior between these, and again that will extrapolate down to V threshold. So in the two different regimes, below saturation and above saturation, you can make two different plots to find the threshold. And the let me complete that. So the slope is given by the square root of mu Cox W over 2L. So in either case, you should be able to determine some of the parameters. Now, you'll notice that in either case, above or below saturation, most of these parameters are geometric, and the mobility is the one that is kind of most sensitive to material quality, and so either of these can be used to find the channel mobility in either below or above saturation. Okay, so let's look at two other definitions. So the transconductance G, this is dI versus dVGS, the slopes that we were just looking at, the slope we were looking at below threshold. And again, the transconductance is what this quantity is called. And remember, if we go back to our definition, we have G times V gate source. The next thing I want to talk about is the subthreshold swing, or the subthreshold slope. So we started to at least mention this previously, but what you do is plot versus V gate source. You plot on a log scale. So previously we plotted on a linear scale. It took a extrapolation to find V threshold. Now if we go on a linear scale and look at the region below V threshold, we'll have some region where this is linear. So let's just draw VT here, and just note that we're sort of to the left of the region we discussed before. So on this plot, the slope we want the slope to be as large as possible, meaning that we can change the current by 1 decade with the smallest possible voltage. And it turns out that the theoretical smallest number you can hit is about 60 millivolts needed to move 1 decade. So, and that comes from the natural logarithm of 10, which converts you between ln and log base 10, and then times the thermal voltage. And in the next chapter, we'll see where this comes from when we discuss the subthreshold leakage current or subthreshold conductivity. We'll physically discuss this, but the number that you're looking for if you're trying to make the best MOSFET possible will be to push that subthreshold swing, which is 1 over the slope, towards this 60 millivolts per decade. So again, the swing is given in voltage per decade of current. The slope of this plot over here that we made obviously is in decades per volts. Okay, the last thing to discuss is the effect of biasing that body. So let's draw our structure again. We've got our gate, our source, and our drain, and this is the body here. So what we can do is sort of add to the gate voltage in a sense. So the body voltage sometimes called base voltage too. It sort of adds to the V gate, but excuse me, let me erase that we're no longer assuming that we're grounding it. So it's not quite the same effects because it's changing the relationship between the source and the base now. Previously we were assuming that they were both grounded. So the main effect is that it's going to change the threshold voltage around. So if we plot the V gate source and versus square root of the current, so this is in the saturation regime. What we'll see is a family of curves. So this is the original V threshold, and if we apply a positive body voltage, so this is 0, VB greater than 0, we'll change the threshold voltage. And that threshold voltage change is derived in the book and given by this formula here. So square root of 2 times the electron charge times the dielectric constant of the semiconductor times the doping. So basically this form tells you that it has something to do with the depletion width changing over C aux, and then times the quantity that I'm going to move down in brackets here, square root 2 phi fp plus V V base minus square root of 2 phi fp. Okay, so what you can do is get a little more control over your channel charge by using that fourth terminal, that base, to sort of add and accentuate the effects of the gate. Alright, so we've in these two videos here we've gone through and sort of seen the basic current voltage curves of the MOSFET. We've looked at sort of phenomenology and looked at the equations that govern the source drain current as a function of source drain voltage. We've seen how the gate voltage affects things in terms of changing that channel charge and moving you above and below threshold to turn the device on or off. We've also added this new concept of saturation, where the source drain current rolls over and becomes constant because of the pinch off in the channel. Then we've looked at the transconductance to find it, also the so-called sub-threshold swing to find that, and then lastly looked at the effects of using the fourth terminal, the backside or body voltage that you can apply to the wafer itself to sort of help the gate do its job.